Only you present? Is it? Or you pass
No,
around?
four of us.
Or four
Yeah,
of
pass
you?
around.
Okay.
Yes, sir. Okay, so can we start?
Okay.
Am I? Okay, let's go. All right. Okay. So,
Oh, leng chai.
Eugene, open your camera. Eugene, open your camera.
No,
a
I talking
very,
also little lah.
hey, listen to my presentation, okay? So, very good evening. Very good afternoon to to my fellow friends and Mr. Salfi. Today we are going to be presenting, me and my group is going to be presenting about conduction. Interesting, right? Conduction. So what is conduction? Let's go to the first slide. Sir, can move. Okay, so heat is an interesting form of energy. Not only does it sustain life, it makes us comfortable and help us prepare our food, but understanding its properties is key to many fields of scientific research. For example, knowing how heat is transferred from and the degree to which different materials can exchange thermal energy covers everything from building heaters and understanding seasonal change to sending ships into space. So we can see that heat has many, what do you say, interesting form of energy. Okay.
Can I
So,
disturb for a while?
can what?
Can I disturb for a while? If according to thermodynamics, heat is not a form of energy, right? Heat is the transfer of energy.
Can let him finish the presentation later you ask.
Okay.
Okay.
Can, chill lah, wait lah. Okay, so heat can only be transferred through three means: conduction, convection, and radiation. Of these, conduction is perhaps the most common and occurs regularly in nature. In short, it is a transfer of heat through physical contact. It occurs when you press your hand into a window pane, or when you place a pot of water on an active element, and when you place an iron on the fire. This transfer occurs at the molecular level from one body to another. When heat energy is absorbed by a surface and causes the molecules of the surface to move more quickly. In the process, they bump into their neighbors and transfer their energy to them, and a process which continues as long as heat is still being added. Okay, let's move on to our next slide. So next is heat conduction through solids, that is conduction. So as you can see, the diagram shows the heat conduction to solids, that is conduction. And you all can read that. Do I have to present that also? Okay, I'll just read it out lah. So the molecules in solid vibrate about their own equilibrium positions at room temperature. The vibrations of the molecules approximate simple harmonic motion. At the hot end of solid, the molecules with more thermal energy vibrate vigorously with greater amplitude. The molecules impart the vibrations to adjacent molecules via intermolecular forces between molecules. The hotter molecules collide with colder molecules. Okay. As a result, energy is transferred from the molecules at the hotter region to colder region. Okay. So next is collisions of electrons. So, can change slide. Oh, okay. So when a solid is heated at one end, the atoms there vibrate with more vigorously. The free electrons which collide with these atoms gain kinetic energy. The free electrons with greater kinetic energy collide with slow-moving electrons and other atoms from the colder region. As a result, some energy is transferred to slower-moving electrons. Energy is transferred from hotter region to the colder region of solid through random collision of electrons. This method of heat transfer is known as electronic conduction. Since electrons are lighter and move faster, the transfer of energy, though electric conduction is greater and faster compared to lattice conduction. A good conductor of heat is also a good conductor of electricity. Metal conduct heat through lattice vibration and collisions of free electrons. Non-metals conduct heat through lattice vibration only since it has free electrons. Therefore, non-metals are generally poor heat conductors. Next slide is difference between lattice conduction and electronic conduction. And y'all can see the table. I don't. Okay. So next is defining thermal conductivity. Okay. So the process of heat conduction depends on 4 basic factors: the temperature gradient, the cross-section of the materials involved, their path length, and the properties of those materials. And you can see the diagram shows heat conduction occurs to any material, represented here by a rectangular bar. The rate at which it transfers depends in part of the thickness of the material. You can see the... Hey, what are you all chatting? Okay, so the next slide. Okay, this is the formula. I mean, the slide explains how it's done. So you can observe. So you can take note that the instantaneous temperature gradient at any point equals to the rate of change in temperature with distance along the block. And the formula is given below. And the unit for temperature gradient is, you see yourself lah. And the temperature gradient has negative sign is due to that the temperature decreases as the distance x increases. And the diagram shows the picture of a block of metal between two hot and cold objects insulated from its surrounding. So yeah. Okay, we can go to the next slide. Okay, you all can observe this also.
Have we have the same screen, Sujam? Right?
Yes, sir. Same screen.
Okay.
Yeah. So you can see like temperature gradient. The greater the magnitude of the temperature gradient, the greater the rate of heat flow. In the cross-sectional area, the larger the cross-section area, the greater the rate of heat flow. And for the material of the solid, iron is a better conductor than a brick. Hence, the rate of the heat flow is greater in iron compared to the brick. Okay, so with the next slide. Okay, this is the equation and everything you can see. Okay, so next slide. Defining thermal conductivity. Next slide, sir. Okay, so thermal conductivity is the ability of heat transferring heat through an object. As saw from Fourier's law, the larger the value of K, the larger the value of the, you see that lah, while other factor being constant. Therefore, good conductor of heat such as metals have higher value of K. Weaker conductor of heat have a lower value of K. In some cases, while some metal was heated, the value of K decreases slightly. And the next slide, sir. Okay, this is a table of thermal conductivities for different kind of materials. This is also in the textbook, like you can see. Yeah. And then thermal conduction in perfectly rod, I would like to pass it on to Mayway. Mayway will continue with thermal conduction in perfectly insulated rod, thermal resistance, and that's all.
Maybe, are you there?
Maybe.
Maybe. Hello, maybe, are you there?
Yeah.
Okay. This is your slide, right? Okay.
So Thermal conduction in perfectly insulated road. Next slide. The temperature at M and N are maintained at theta 1 and 2. Accordingly, the temperature at different points of road are changing with time. The rate of heat flow dq over dt is constant at every point along the road. According to Fourier's law, the magnitude of d delta over dx is a constant since k, a, and d delta over dx are constant. In this case, d delta over dx equal to negative delta 1 minus delta 2 over L, smaller than 0. From equation dq over dt equal to negative ka d delta over dx equal to ka delta 1 minus delta 2 over L. For root of length L with a uniform cross-section area A and constant heat flow, then Q over T equal to Ka delta 1 minus delta 2 over L.
Next slide.
Yeah, next. So, thermal resistance is a heat property and a measurement of a temperature difference by which an object or material resists a heat flow. Thermal resistance along a conductor is very similar to the flow of charge in an electrical conductor. Potential difference is needed for electric charge to flow. Temperature difference is needed for heat to flow. Hence, analogous quantities for the two flows can be ascertained by comparing the equations. So the rate of heat flow is dq over dt equal to Ka delta 1 minus delta 2 over L. So equal to change of delta over L over Ka. The rate of electric charge flow is dq over dt equal to delta A V1 minus V2 over L equal to V over R. Thus, the change in delta is analogous to V and L over Ka is analogous to R. The term L over Ka is known as thermal resistance. The unit for thermal resistance equal to L over Ka is Kelvin per watt. Finally, the rate of heat flow can also be written as dq over dt equal to change of delta over thermal resistance. The two ends of the root are maintained at temperature 1 and 2 respectively, so some heat escapes from the side of the root into the surrounding. As such, the rate of heat flow decreases as x increases along the road. The temperature decreases as x increases along the road. From the rate of heat flow, dq over dt equal to negative ka d delta over dx. K and a are constants. As dq over dt decreases, the temperature gradient d delta over dx also decreases as x increases along the road. Temperature fall is the steepest at the hot end. So this is next. Eugene or Janice? Janice.
Where's Janice?
Janice.
Is he here? Janice? He's missing.
Hello.
Okay.
Yes.
It is supposed to be mine, but okay.
Teacher, I thought mine was previous one, but then maybe
Okay.
say everything already.
Okay. Okay, your
Never
part.
mind, you say again.
Okay, I can say again if you want.
Okay, Janice.
This one is the question. So next,
For next. Okay. What is this?
yeah,
Oh, next.
it's
There I don't need to present lah. Okay lah, ons lah.
yeah, day
Good night,
teacher.
guys.
This one is supposed
Good
to be
night, guys.
Eugen's one.
Okay, so this question is about.
It's about the temperature at the junction.
Hmm.
Find the temperature at the junction using the gradient of ice equals to gradient of wood.
So next slide. Okay.
Yeah.
So you want to present this one or what? Oh, base writing. Okay, what is this? Janice?
Yes.
What is this?
This is finding the temperature at the junction.
Okay, between the ice and the wood. Is it wood?
Yes. Wood.
Okay. So where's the temperature? Where's the junction?
The
Where's
junction is at the is at the middle one.
middle over here? You mean over here?
Yeah.
This part. Right.
Yeah.
Okay. So this one is what? Above and below.
Is it cross sectional?
No, I mean there's a blue thing.
Heat flow.
Heat flow.
Heat flow.
Maybe. What is these two things actually?
Insulation.
Ah,
Rod.
insulated.
Insulation.
It was insulated by these two blue. So that's why we can
Yeah.
find the junction over here. Okay. Next. Okay, Janice, are you going to read
Yes.
or you want only to
Okay.
us to see?
So temperature difference. Given that the cross-sectional area is 1 meter square, find the rate of heat flow. To find it, it's temperature difference over total thermal resistance. Yeah. The working is like this.
Now Eugene explain what you know.
Hey, what I know Okay, I explain. Ayo, wait,
Okay.
let me see Uh, wait, sir. Let me think first.
No, I'm watching Bay. Bay's making one question, big question. Question mark
This
there.
is a question, sir. Oh yeah, this is a question. So this is an example of the question of how to count the rate of heat flow. What is lol? So to count the rate of heat flow, you need to take the temperature difference, which means when the temperature when you heat when you heat one side, that temperature, and the temperature when you heat the other side. So the temperature difference when there's both sides over the total thermal resistance, which means the resistance where you need to count the latent heat over the thermal, that constant thingy, the K, which is given over here. Yeah, like sir is showing in the screen, the K wood and K ice. So that is the thermal resistance. So you count the it's a formula lah basically. So can you go back to the last slide? So this is the formula lah. So the only way to do this is if you memorize lo. Good luck guys, exam. So that's it, I think. Is this the last slide?
Oh, last. Okay.
All right. The end. Thank you all
Okay.
for your listening. Today
Hey.
got no homework. You guys may go
Is
back.
it me or is it hot in here?
Okay. Okay, Ken want to
Okay,
ask a
Ken.
question.
What's
Ken
your
want to ask
question?
question. Going to the first. I think he's going to the first slide.
Ayo.
Mic Pro, wait. Depending on what you ask, your screen might go black.
Faster Ken, faster.
Okay, settle. What?
Just now I remember what Jared said. What the definition for heat?
Yes, heat is a
Jared,
form.
can you?
Heat is a form of energy, right?
But how if I want the exact definition according to thermodynamics?
The one textbook got I think. Wait
Gerard
What's
has
your
to
question?
answer. It's Gerard has to
Yeah,
answer,
what's
right?
your question? What's your question? Ken?
What is the exact definition for heat according to thermodynamics?
According to thermodynamics. According to thermodynamics.
Yeah.
Okay. In thermodynamics, heat is energy transferred to or from a closed system lah. So by mechanisms other than thermodynamic or transfer or matter. The various mechanisms of energy transfer that define heat are stated. Like
So
in
what
the
I
first,
have to correct here is heat is actually not the form of energy. Heat is actually just the transfer of energy.
Yeah. In thermodynamics.
And exactly when we bring to physics in future, every time physics is not anymore.
Basically, it's a transfer of kinetic energy from one medium or object to another.
Okay,
or from
so the
energy
correction.
source to medium or object.
Okay, so basically the correction here is heat transfer is a process. Like heat is a process lah, more of like a energy transfer. And well, how to say Yeah lah, so basically heat is basically just energy transfer. It's not a form of energy lah, as what Ken said. That's the correction here, right?
Where yeah, true.
Okay, Kao team, anything else?
I'm reading. Wait for me for a while.
All right.
I think no problem.
Okay, sir, any questions?
You see, heat doesn't exist objectively, It's a perception. Neither does energy exist objectively. It's a concept. Unless you're a theoretical physicist, walk away now. One of the other answer would be more suitable.
So
Okay, from the presentation, okay. I think the slide over here, this one is good. Okay, explain everything about the collision of electron. This is very important. the collision of electrons when it's without the free electrons, such as wood. Okay, and this is with free electrons. Okay, so it is important that these free electrons, this is the one who can transfer the heat very fast. This is the one you can goes very fast to other side of the end of the rod. Let's say it's a rod as for example. Okay, so there's a very big difference. If you have a conductor and non-conductor, non-conductor doesn't have any free electron, where a conductor has a free electrons. So yeah, both of them actually. Okay, if I show if it was we are all in the class, if I have two rods, one is made from the wood, one is made from the metal or conductor. If I give you uh rod at the same time, when you're holding the both rod at the same time, which one you feel colder? Anyone here? If I give you two rods, one is made from steel, which is conductor, one more is made from the wood. Which one you
Of the
feel much
iron
more
one,
colder?
the metal,
The metal. Why?
the transfer of heat is faster.
Yeah, the transfer is faster. Although is if I take a thermometer and I put the thermometer on the wood and put the thermometer on the steel, both of them have the same temperature actually. If I have a laser thermometer, okay, one I shot at the rod with a metal. Let's say both of them have the same temperature like 35 or 36. Okay, both of them the same temperature, but when you hold it up, you feel that the the metal rod has much more colder than the wood conductor, wood rod. Okay, it's because the heat transfer, your body heat came out, transferred faster out to the air surrounding you. Okay, so this is about the electron. So lattice conduction and electronic transition has its own difference. Okay. Uh, so electronic
So
yeah.
now I realize that
Mm.
about the thermal conductivity of poor conductor, the least method.
Least
Least method.
least method. Seriously
Yeah.
or seriously method.
LEE.
Least method.
Least method. Yeah. Not in the slide.
No. That is not. It was in the STPM, but it's not. It was not right in the new STPM. It was there.
Oh, it was there before.
It was there. In the old STPM. No. Even though we have a experiment on the least method, but since the modular STPM we don't have anymore least method.
Okay.
Okay. Focus on the non-metals. Okay, having thermal conductivity area. Thermal conductivity area. Okay. So what's the main formula, correct? Eugene? The main formula for thermal conductivity? Actually, I told you to bring up two examples, right? And two examples with the answer. But you only bring one examples with the answer. So Gerard, what is the main most important formula in thermal conductivity? Gerard, are you there?
Yes, sir. Wait, I see.
We only have 4 minutes, faster.
Teacher, his makeup lah.
Okay, what's the most important formula in conductivity?
Gradient.
What is the most important?
Delta. Temperature.
What's the most important formula? Yujun.
Rate of heat transfer.
Ah.
The one on the screen that you
Yeah.
write lah, right? The one lah, sir.
Okay. That's nice.
So now thermal conductivity equals to amount of heat transferred, then distance between the two isothermal planes divided by area of the surface and difference in temperature.
Yeah, it's this formula lah, right?
Okay. So Q dt is what? Q dt is heat over the rate of heat
rate
over
rate of heat over time lah, rate of heat lah.
rate of heat. This
Change
one,
of energy over change of time.
this one,
That's change of temperature over what's x?
change of temperature over change of the distance x.
Distance.
X. So you see the distance over here, this one, d, this distance, this is the x. Okay. Okay, so we have a good data.
So isn't there a negative sign in the formula?
Yes, it should be, because as the x goes towards the left side, as the x no, the q going to the left side, it will be much
Decreases.
more further. Yeah, the temperature much more decreases. So that's why we have negative. Okay lah. So giving this one, perfectly insulated rod, because of the heat does not goes out of the rod, so only heat goes from the left to right. So we have the gradient will be equal. K will be equal from left to right. But where's the non-insulated? When the non-insulated means that the heat can goes up and down. The heat can goes up to the surrounding. That's why the K will be not constant. See, the temperature drops down. Okay.
Right.
So that's the difference between non-insulated and insulated rod. Usually the question we ask about insulated because it's hard to find a non-insulated rod to calculate non-insulated rod. It can be two junction also. One material, a question can be one material, second material, and the third material over here. So material number 1, material number 2, material number 3. They ask you what will be the dq over dt of these three material. So you have to calculate 1, 2, 3 material over here. Okay, I'll put some of the question on the Google Classroom, and then you can try to answer it. Okay. So time's up already.
I think.
Less than 1 minute.
No.
We have less than 1 minute. Okay. See you again tomorrow. Bye bye.
Okay, sir. Thank you, sir.
Okay.
Bye.
Tomorrow,
I will
Not
post
today.
the video later.
teacher, not Thursday, meh? Tomorrow where got physics?
Huh?
Tomorrow,
Tomorrow is
Wednesday.
for upper 6. Upper 6.
Oh,
Okay, okay.
Tuesday. Oh,
Upper
six.
6. Okay, okay.
Tomorrow,
See you
Wednesday.
on tomorrow, Wednesday, Thursday. Okay.
Thursday.